Dependency parsing can be cast as an combinatorial optimization problem. So in this formulation, we say that we have a sentence X and we have a set Y of candidate dependency trees for the sentence. And the problem that we want to solve is we want to find a highest scoring dependency tree Y hat from the set of candidate trees. And we do so by computing a score for candidate trees. So a score of X and Y will give us a score for each combination of a sentence with a candidate tree. And we want to find the highest scoring tree among all possible candidate trees. The computational complexity of this combinatorial optimization problem will depend on the choice of the set Y of candidate trees and of the scoring function. In this section, Y is the set of all projective dependency trees. So every projective dependency tree will be a viable candidate tree for the sentence X. Regarding the scoring function, we will be using a very simple scoring function, which is based on what is known as the arc-factored model. So under the arc-factored model, the score of a dependency tree is simply the sum of the scores of its arcs. So if we want to find Y hat, the highest scoring dependency tree, we can maximize over all possible candidate trees. And for each candidate tree, we simply loop over all the arcs in this tree, compute the score of each arc, and then add them together to get the score of the complete tree. The score of an arc then is defined as the dot product of a feature vector and a learned weight vector. So the feature vector will basically be translating the arc in the context of the sentence X into a vector representation, and then we will have a matching weight vector where every feature in the feature vector gets its weight, and then we will be multiplying these two together to get the score of the arc. This is the arc-factored model for dependency parsing. And I will now be presenting two algorithms to solve this combinatorial optimization problem of finding the highest scoring projective dependency tree under the arc-factored model. And the two algorithms are the Collins algorithm and the Eisner algorithm. Both of them solve this combinatorial optimization problem using dynamic programming, and more specifically using bottom-up dynamic programming, where the score of a tree is broken down into the scores of smaller subtrees. And the basic structure of the algorithms will be to first compute the score of the trivial trees that just consist of a single vertex. And according to the arc-factored model, the score of these trees is necessarily 0 because there are no arcs that could contribute anything to the score. And then the algorithms will combine these smaller trees into solutions for larger trees. And eventually, in the end, we will have one large tree that covers the complete sentence. And if we have found that tree, we have found a solution to our overall problem. So the basic structure of the two algorithms is the same. However, the two algorithms differ with respect to the specific strategy in which they decompose a problem into smaller subproblems. And correspondingly, they will also differ with respect to their asymptotic runtime, which will be very important for practical applications.